Okay, so here is the summary of last time. So so in the last lectures we discussed first of all the representation of the ratio between interacting and non-interacting dimer partition function as a quartic sort of phi-4 Gaussian integral. So this is the original object we want to compute. This interaction is a quartic interaction that here I represent symbolically like this. I have a set of 4 indices associated with the fields, the Grassmann variables exiting, well, psi plus, psi minus, so I'm thinking of exiting, entering, in this sense. And this is a way of representing the plaquette interaction. Here is a symbol for it. This psi of p is just a short way of writing the product of the 4 fields labeled by these field labels. So this is 0 psi. Okay, and so this is after having rewritten psi in terms of these quasi-particle fields. The quasi-particles index is this omega here. This reference Gaussian integration has a propagator given by this object here, where mu of k is just the Fourier transform of the Castellan matrix, and p omega are the singularity points, known as Fermi points, and the behavior of this dispersion relation close to the singularity points is linear with a specific behavior written here. So from now on, I will represent this linear part of mu as d omega of k. So this is not exactly d omega of k, it's d omega of k plus order k squared.
You have the staggering factor if you write like this, no?
No, because I already. So this is the omega. So yeah. I would have the staggering factor if I wrote the original field in terms of these guys. But this is now reabsorbed into this. So this v now is the original product of delta function telling that these 4 axes are next to the 4 vertices of a plaquette times the e to the I p omega x that came from the composition of psi into quasi-particle. Okay, next I decompose in a multi-scale fashion the propagator. So if I do it up to a certain scale h, at each step I replace. So for instance, at the first step I replace. I add and subtract the same characteristic function computed in 2k. Then this is the single scale support function, and then I repeat adding and subtracting I of 2 to the 2k, and so on, and I get a number of single scale propagators that have a natural scaling property at dominant order. So if you could replace mu exactly by this linear part, they would be exactly scaling. They are not exactly scaling, but almost so when you go on with the scales. And we described an integration procedure, including use of the determinant formula to compute in form of a convergent power series the kernels entering the definition of the effective potential on scale h. So the effective potential on scale h has a structure that is very similar to the original one, with the important difference that the original one was exactly quartic. Now this is you have all possible. Now p is not forced to be a set of 4 indices, but it can have 2, 4, 6, 8, whatever number of indices. So this is formally a series of this sort. But the good thing is that we have explicit bounds for these kernels that modulo some problems that now I will rediscuss are local on the right scale. So the original was local on the scale of the lattice. These guys are local on scale 2 to the minus h, which is the right thing. So the bounds that we discussed are L1 bounds that can be easily adapted even if I didn't discuss the detail of this adaptation. They can be easily adapted to a weighted, exponentially weighted L1 norm. And the bound we obtained has the following form. So here we need, of course, a bound on the original quartic interaction, which is this, where alpha is a small parameter. It measures the strength of the interaction in the dimer model. And this, of course, enters this multi-scale bounds. So here you have sum over trees belonging to a set of trees with a root on scale h and n endpoints. So graphically, we represent them this way. And all these trees go on until they reach scale 0. So they branch, and at a certain point they reach scale 0. So these trees are characterized by a sequence. Okay, and this n stands for the number of endpoints. Each endpoint is associated with one of the bare interactions. Each of these branching points is associated with the action of so each of these branching points, I denote them by V. They come with a scale, and they represent the action of a truncated expectation on scale HV. The truncated expectation acts on the values of the subtrees exiting from branching from this node. And the kind of bound we discussed last time is of the following sort. So for each of these guys, which comes with its own scale label, we have to sum over all possible choices of Grassmann fields that are still to be integrated at that level. And the condition is that at the final step, the fields that still need to be integrated are exactly L, where L is the field label of the. So in this case, L is 6. So at the last level, PV0 should be 6. At all the other levels, it should be an arbitrary choice compatible with certain constraints that come out of the analysis. Okay, and we have this kind of remarkable bound. So we have an overall scaling factor, 2 to the h times 2 minus L over 2. And then we have V product over all the branching points. 2 to the HV minus HV prime, 2 minus PV over 2. So
you have alpha to the power n or alpha to the power 2n? No.
N. We have n endpoints. So for each of these guys, we have a bare interaction that has normal alpha. So this 2 minus number of Grassmann fields divided by 2 is the so-called scaling dimension. of an effective interaction with L Grassmann fields. This under this and this V prime. What is V prime? V prime is just the, so if V is this one, V prime is the parent of V on the tree. So it's the, okay. And so this comes out naturally out of, if you like, of natural rescaling that is induced by this procedure okay, so you see it's the same guy as appearing here with the scale difference that is what you naturally get when you go from one scale to the next one. So this came, this came naturally out of the, we didn't make any explicit rescaling, I just made the bounds, and this is what happened. Okay, so this shows already something interesting. So first of all, it tells you that if you restrict the sum to PVs that are all, so sum restricted, of course the sum restricted to certain to some PVs does not reproduce the correct total effective potential, but okay, it's still a sum of infinitely many Feynman diagrams if you look at it. So if you restrict the restrict the sum to this set of choices of PVs, the sum is exponentially convergent. You see, so this guy is by construction a positive scale jump. If PV is larger or equal than 6, this is smaller or equal than -1. So these are exponentially decaying factors. So essentially, this the only trees that will really count are the short ones. The long ones will have a sort of exponentially decaying. No, but okay. But they need to be long because they reach scale 0. So essentially you have an exponentially convergent sum. Okay, but the problem is that we really have cases in which PV is equal to 4 or PV is equal to 2. So if PV is equal to 4, this is 0, and this produces a factor that tends to grow with the length measured in scales of this guy. And if PV is equal to 2, even worse. So it grows like 2 to the h, the contribution associated to these guys. So there are problematic terms coming from so the subdiagrams in which you have the external lines that are on scale HB prime or lower, and whatever is inside is of scale larger or equal than HB. And similarly for the 4 leg diagram. So we want to understand how to deal with this. How to deal with these guys. So let me start the discussion. So this is sort of the very important aspect of the theory. So let me start with the two-leg guy. The two-leg guy is something of this form, say. Okay, with some indices. Okay, no, the indices are just these ones. Something of this form. Maybe not. Maybe this H is the same. Okay. Let me not have it. So this is a kernel in which inside there are propagators of scales larger or equal than HB, while these guys have scale smaller or equal. So let me. convolution of propagators on scales larger or equal than hb. Okay, okay. Yeah, I'm not sure I'm completely consistent with the notation above. Okay, anyway, no, maybe it's okay. No, I think it's okay. Okay, so what do we do? So this guy tends to produce dangerous scaling factors. So let me look into the divergent contribution associated with this. So the first thing I want to do is to extract a really divergent part from this in order to be able to analyze it more closely. So what I will do is to rewrite this guy as local part. So this guy is essentially local on the right scale. So I want to, so if I extract its local part in a very natural sense that I will now describe, this I expect it contains most of the problem. I mean, the non-local part, since this is exponentially decaying on some scale, the non-local part should have some better behavior. This is in fact what it turns out to be. Roland, there was a comment?
So h is negative for you, so scales bigger than h means shorter distances than...
Yeah, exactly. Yeah, this is the log of the scale. I think it's... okay, no.
Yeah, no,
okay. So, what is the local part? The local part is defined in a pretty natural way. Let me define in the first way that I will have to adjust in a second. So this local part will just be the sum over y prime of delta xy. So essentially, I take a really local object with intensity given by the sum of this guy. So this is a pretty natural thing. This is nothing but the Fourier transform computed at k equals 0. Okay, the sum over all core. This is translational invariant, so it's a bit like. Okay, this is also the same as replacing the guy upstairs by sine plus x w2 omega xy sine minus x. So this replacement is the same as this. I mean, I use the delta function and I rename y prime, I rename it y. So it's the same as replacing the second field, say, by the same kind of field, but computed at the same location of the initial one. So okay, what did I want to say? Okay. So the first thing I want to say is that this guy, if you look into it, I have no time to do it now in detail, this is equal to 0 thanks to lattice symmetries. Remember that this is the isotropic model, the one that I'm studying. So this is reflections about horizontal vertical planes. Discrete rotations. So this is the same kind of cancellation that I emphasized a few lectures ago. The one that was telling you that if you sit down and compute the value of this diagram at p equals 0, you get 0. I mean, this is just a symmetry. And this symmetry is fermionic counterpart of just reflection and rotation symmetry for this. So this is something that you should check, but it's true. So this is the same as the cancellation that I emphasized a few lectures ago. Okay, good. Now what about the rest? So the rest
you already used some symmetry, no? Because you are saying there is no psi plus for its obvious.
Now that is, yes, that if you like is a symmetry, but it's obvious because the original interaction add as many pluses as minuses as upper index, and every time you contract, you're pairing a psi minus with a psi plus.
So is this
So you have particle number conservation.
So is this the mass? So does this mean?
No, this would be if you add this guy, you would just you actually would just change the location of the singularity. Would not be a big trouble, but would complicate a bit the discussion. So I want. You see you have something like minus I minus 1 k1 plus minus I plus 1 k2. If you produced something, this would just change the location of the zero. So if you produced a small complex value here, this would shift the location of the singularity.
But doesn't this mean that if you don't shift, you have a mass?
No, no. I don't.
So, but it's a quadratic term in the field, right?
Yeah, but it's a chemical potential term. It's not a mass term. So it just means that if you generated such a term and you would be so naive to continue to so you are producing a shift in the singularity. If you insist in perturbing around the propagator in the wrong place, you get divergences that are sort of.
But then you get exponential decay because you're not at the singularity. Is that right?
No, you just get divergence of the series. You don't get exponential decay. No, it's not the same as having. No, it's not a master. It's a shift in the location of k. It's not a shift in the critical temperature. We can maybe discuss this.
But isn't that
perhaps it's a little bit like having. Perhaps it's a little bit like having a magnetic field in a Bose gas. I mean, that would shift the minimum of the potential.
Maybe. I mean, a mass term would be plus minus in the omega indices, but here you cannot have for momentum conservation reasons. More questions? Okay, so what about the rest? So I extracted this local part. I want to argue that in fact the rest is better behaved. Why is it better behaved? So the rest is is this expression with here the difference between psi y and psi x. So what is this? So this is approximately, so today of course I cannot really measure how possible. This is essentially this thing here. So where by this deep psi I just mean the Grassmann propagator that when the Grassmann field that when contracted with something else produces a propagator that is the derivative. Okay, so what's the if you like, you have an extra term of this sort. So this y minus x goes together with this guy, but this guy, if you remember, was exponentially decaying on scale, scale hv. So this guy here, when you put together with this guy, you can add and multiply. So you say that this is the natural a-dimensional object, and you're left with this dimensional factor associated with this guy. Does this make sense? What about the derivative? The derivative acts on a field that has scale smaller or equal than hv prime. So this, remember, the propagator of this, so this is a field that is whose propagator has natural scaling properties. In particular, it lives on scale 2 to the hv prime x. So when you derive, you pick up a factor that is 2 to the hv prime. Is this clear enough? So I'm using the scaling properties of the propagator that I discussed in the previous lectures. So if you put together this guy and this guy, you see that this extra y minus x times derivative dimensionally induces an extra dimensional factor of the form 2 to the minus hv minus hv prime. So you see this goes in the right direction. This hv minus hv prime is like that guy there, and we have a minus 1 there. So this effectively subtracts a 1 inside the parentheses. So we started with something that was exponentially increasing. After the subtraction, we get something with a 0 in parentheses. So we are in better shape. Not completely done because we have a 0 there. So we repeat this kind of idea. So we repeat this kind of idea, and we refine, if you like, the definition of local part. So the refinement is the following. So instead of defining a local part in terms of the replacement psi minus y into psi minus x, we subtract also the first subdominant part. Okay, so this was the responsible of the first local part that was 0 by some lattice symmetries. This guy now is another contribution to the local part. What's the structure of this? So let me look at it. This is y minus x d minus x w 2 omega xy. So now see that y appears appears only, so this is translational invariant, y appears only here and here. So after the summation, this becomes something of the following form. Where zeta is the result of the summation we did. It's a two-component guy. Remember, here we are in 2 dimensions, so this is a two-component vector. This is the two-component gradient. Okay, so this in Fourier space, this is just minus I. Omega minus k, and again using lattice symmetries. This is again something one has to sit down and check. This is minus zh b omega. So it is and this zeta of h is a real. So this is a symmetry, again a sort of symmetry cancellation. So you have, in general, 2 parameters, zeta 1 omega k1 plus zeta 2 omega k2. Using the lattice symmetries, one can see that this is proportional with real proportionality constant to the original. Remember, d omega of k was the linear part. Was the real part, the linear part of the dispersion relation around the singularity points. So this is not a priori obvious, but this has exactly the same structure as the inverse propagator. So you see, this has exactly the same structure of what you have in the Gaussian reference part of the measure. So the idea is that you can now insert this step by step into the reference Grassmann Gaussian integration that okay, I erased now. And as far as the quadratic terms are concerned, we are only left with the rest. Now the rest, what is the rest? So the rest is now improved by this additional subtraction. So now this behaves essentially as y minus s squared gradient squared sine. And for the same reason I told you before, now this is dimensionally something of this form. So now this minus 2 really cures the divergence problem for the quadratic terms. So we are happy. So once again, we had these quadratic terms and potentially producing divergent contributions. We look into them by extracting the really divergent parts. The really divergent parts are those associated with this replacement and this replacement. This by symmetry is proportional to 0. Good. This by symmetry is proportional to the linear part of the Gaussian reference integration, and we combine it with. So this corresponds to the resummation of the chain diagrams that I mentioned a couple of lectures ago in this multi-scale framework. So if we do that, we are moving some of the potentially dangerous part in the propagator, and what we are left with is well behaved. Okay. Of course, we have to check what's the result of this iterative insertion of these parts into the Gaussian reference integration. This is something I will discuss next. But okay, for the moment, this recognizing a cancellation plus a resummation tends to cure what we, to produce a leftover that is well behaved. So we are happy. What about the quartic terms? Okay, for the quartic terms we proceed in a similar way. So for questions about this?
So d omega k is the propagator, no?
Not exactly. So the real propagator, remember, in Fourier space was this one.
Yeah.
So this was d omega k plus order k squared. I mean, something you can write, but it's order k squared.
Yeah.
So in the linear approximation is the propagator. So this somehow this has the same structure as this part. Remember that if you have a propagator like this means that the Gaussian integration, the reference Gaussian part, is what can be written this way. Plus this, let's say, this rest. Remainder, sorry.
You can do the opposite, no? You could write d as a mu, and
yes. Okay, I don't know. Yeah, you have. Of course, you have freedom in this. So the freedom is in the fact that you want to just deal with the divergent part. So first, the divergent part is defined modulo convergent part. So you have some freedom. So I don't know. The choices we did are these, but yeah, you can add them, subtract mu. Okay. What I'm saying, so you see, you have this is the reference Gaussian integration we have from the beginning. The term we are producing is a quadratic term of exactly the same form. So the idea, you plug in here and you can insert, so here instead of having a prefactor 1, after the resummation you will have a prefactor. And you want to do this at all steps. So at the end of the day you have to discuss what is the fate of this this prefactor that you are changing step by step.
But this prefactor is not just 2 to the power h something?
Okay, it will. I will comment about it. No, it will be 2. It will now to be 2 to the power h lambda squared. So it's the origin of, because this is at least this order lambda. Actually, it is lambda squared if you try to write the diagram. So this is actually order lambda squared. So you will get something 1 plus lambda squared, and the iteration you will get will be sort of multiplicative iteration. So it will tell you that okay, you help me because this is already part of what I was planning. So if you insert this at each step, you get a multiplicative recursion that as a solution has something of the form 2 to the minus h constant lambda squared. So this will tend, so you say you have a propagator that initially has a pole singularity, so on a single scale is 1 over 2 to the h. After this resummation, it will become 1 over 2 to the h 1 plus lambda squared. So this is the origin of one of the critical exponents that appear in the theory. This systematic way of proceeding is a bit like resumming systematically the logarithms that I was mentioning on Monday, but resumming them in a smart way so that they produce an anomalous power law rather than an apparently divergent logarithmic series. Okay, very good. So you now you essentially know the solution for these quadratic terms. What about the quartic terms? So these are more problematic, because you have no way of combining them with the quadratic, but they are not quadratic, so you really have to live with them. You cannot. So the quartic term have. Okay, so now I want to do the same kind of strategy. And the strategy will be the following. So it will be again an extraction of a local part. The local part, I hope now the idea is relatively clear. This is replaced by all the guys located at the same place. Say for instance at the location x1. You have again some freedom. You could choose instead of x1, x2, and nothing will change. Okay, note also that since these guys are Grassmann, the square of a Grassmann variable is 0. So in order for this object to be different from 0, you need to have these two indices different from each other, and these two indices different from each other. So it means that up to a permutation, this should be x1 plus psi minus x1 plus psi plus x1 minus psi minus x1 minus. Okay, the rest, not surprisingly, I won't repeat but the argument is exactly the same. The rest remainder, I think, is RW, the so-called irrelevant part, comes with an additional HV minus HV prime compared to the estimate you would get for the quartic term. So you see also in this case when PV is equal to 4, 2 minus PV over 2 is 0. If you have this extra minus 1, this is enough to have a convergent, exponentially convergent factor. So you're happy with this RW. This LW, the local part, we have to live with it, and this is the really dangerous class of diagrams. The good thing is that it has a relatively simple structure. So if you take so the quartic local contribution to effective potential is then of the form lambda h sum over x sine plus x plus where lambda h is the sum over x2, x3, x4 of this guy here. Which is a constant independent of x thanks to translational invariance. Maybe there is an additional factor from the permutations. And again, using the lattice symmetries, you can prove that lambda h is real. This is not a priori completely obvious because your propagators are complex, but you use again lattice symmetries, and this is real. So you see, all the problem is now encoded in this sequence of lambda h's. That if you don't say anything will be typically a sequence that tends to diverge logarithmically. Okay, so far so good. Questions? Yes?
Above was lambda h when you wrote lambda squared? When you wrote the...
Yes. Yeah, in fact, due to the fact that lambda h could diverge, it's not obvious that the iteration of this prefactor really gives this. I mean, the two objects are entangled. So this will be of this form if lambda h remains close to lambda. If lambda h goes to 0, as it happens in 544 infrared, then this would this would actually be 1 plus finite
I have
constant.
the problem with the label h, because the vertex is labeled by h to h of v prime.
Yes, but with the convention I used, I think, if I was not mistaken, for instance, the effective potential on scale -2 has propagators inside that scale at least -1. Remember. So you integrate scale 0.
Yeah, no, but I mean the expression with the v depends on the vertex you are looking at. So
you want an HV prime.
I don't. Or one of the two, I think, does not have to have. I mean, I want the two to coincide. Maybe you put.
Yeah, lambda HV prime. I just forgot this. So this is the same.
So you can put h in both. It's not.
Yeah.
Okay.
Is it fine?
Yeah.
Okay. Okay, so let me now. So this discussion motivates then a reconsideration of the multiscale expansion I explained above. So I should go back and actually modify a little bit the multiscale expansion on the basis of this manipulations that I did at this level. So what do I do? So once again, at each step, I separate for the quadratic and quartic terms, I separate the local part and the quartic part. For them, I extract, I don't know what I said. So for these two guys, I extract the local part and the remainder. local part and remainder. The remainder is well behaved, and I give it with together with the interaction. The local part of this guy, thanks to its symmetry, is resound together with the propagator, and this guy is left as it is. And the outcome of this procedure can be rewritten in the following way. So I get a modified multiscale expansion for the effective potential that is very similar to what I did before. So you notice I could have told you the rules of the right multiscale expansion from the beginning, but for those of you who were not used to this ideas, it would have been appear to be a bit artificial. Now, hopefully, it's not artificial anymore. If what I said makes sense. So the new integration scheme has the following structure. I don't know, we are used I apologize. We use notations where there are some constants that are different. So this is the partition function, has nothing to do with this capital ZH, which is the way in which we indicate this prefactor after scale H. This is a sort of, it's called the wave function renormalization. There is a square root.
While you having P, is ZH?
Yes, so this is the Grassmann-Gaussian integration with propagator. So this has propagator written here as a propagator with the following structure. So it's G smaller equal than H omega X divided by ZH. So this will be the new propagator, the one associated with this, which is dk 2 pi squared e to the minus x minus y ZH d omega k plus this rest of order k squared. So this is the same as the initial one. Okay, so the linear part is dressed at each step, so it acquires a prefactor. The rest, the order k squared term is left as it is. But notice that notice that when h becomes very negative, this is order 2 to the 2h, and this is order 2 to the h, so it's really scales to 0 compared to the first one. V of h has the following structure. So notice that here I write it as a function of psi. Here it's written as a function of square root of z psi. It has the following structure: lambda h sum over x psi plus x plus psi minus plus the remainder part. The remainder part includes all terms with larger equal than 6, and the second order remainder of the term with L equal to. The first order remainder. Here I mean first order with respect to this localization procedure I was discussing before. And now if I write V this way, I get so this remainder part. Notice that this remainder part will not scale to 0 after iterations. It's just something. So it's a bit misleading to think that the irrelevant part, this remainder part, scale to 0 in the infrared. This is not true. So if you look at the fixed point, at what will happen at very deep in the infrared, all these terms will survive. The point is that these terms are all written as convergent series in terms of the parameters zh and lambda h. If you think so there are situations, of course, in which the irrelevant terms scale to 0, but those correspond to asymptotically free theories. This will not be such a case. So if you have a non-asymptotically free theory, so a theory in which the effective interaction does not scale to 0 in the infrared, all the irrelevant terms will contribute to the fixed point.
Why don't you have a minus in front of the VH?
It's a choice.
Okay.
I think I always kept a plus, but okay, you can redefine.
But lambda H has a sign?
Yes, it will be, maybe with the convention I used, at lowest order will be minus 2 alpha.
Okay.
Yeah, so maybe you say it's, okay. Okay, VH will have a structure that has exactly the same, the same form here. And these W's now will satisfy bounds that are exactly the analog of what we had before. So they will be n larger than 1, sum over these trees. Okay, now these trees will have different features. Scale 0 is up here. These trees now will not be forced
These are the bounds for the remainder, what you call the RV?
yes, the kernels of the actually, yeah, let's say they are for the remainder. So let's say these will be for the, say, for L larger than equal to 6, even though even the local part admits similar bounds.
Yeah, I mean you can define RV.
You can also say that. So the point is that these guys will also admit similar estimates. Okay, I will comment about this in a second.
I mean, which guys? There is no other kernels.
Yes, in fact, give me a second. Explain this. I forgot that. Let me explain some. Okay, so first of all, now we have modified trees. Now the trees are not forced to arrive up to scale 0. They can interrupt before. When they interrupt like this, each of these guys will be associated with a dressed interaction lambda h psi Okay, exactly. Yeah, it will be associated. Each of these vertices will be associated with an interaction of this sort here. Just the local part. Okay, the local part is. So you should think of this as originating from the sum of the local part of all the subtrees that were there in the previous representation with 4 external legs. Okay, so the whole local part of all those trees is what I'm calling lambda h sum of psi to the 4. And it appears here. So this lambda h for the moment is a sort of black box that includes all the potentially dangerous contributions with 4 Grassmann fields. Okay, this estimate here. What are these beta PV? These beta PV are these -1 or -2 that I mean the gains that we were obtaining for the remainder with 2 legs and the remainder with 4 legs that we discussed before. So this beta PV is equal to -2 if PV is equal to 2, -1 if PV is equal to 4, 0 otherwise. So once again, these are the factors 2 to the minus HP minus HP prime of the remainder of the term with 4 external lines, and 2 to the minus 2 HP minus HP prime for the remainder associated to the terms with 2 external lines. What about this C lambda square? This is a contribution coming from the rescaling of this wave function renormalizations that we are assuming to be.
So it's also lambda h square. It's also lambda h. Or is it the original lambda? In this
Lambda HP prime.
Yeah, but
Okay, so the estimate above.
in this lambda square it's the original.
So valid the estimate above. No, estimate above. Yeah, the original one. Alpha, if you. Yeah.
No, okay, lambda is fine.
Yeah, lambda 0. I don't know. Where lambda 0 was -2 alpha. Sorry. Estimate above. Valid if this is true. Okay, if you assume something. Oh, okay, so and this is the origin of this 2 to the C lambda squared appearing there. And makes sense. That is, it leads to something summable if lambda h remains small at all scales. Say it's a constant times the initial value. Questions?
So the trees are ending on both 4-point and 2-point functions, right?
No, the 2
No.
points disappeared completely
How, so
because
what
they
was-
were summed into this guy here. So the new propagator has this structure
Right.
that originated from the fact that the local part with 2
Yeah, I
legs.
understood that. So is that's the new propagator?
So sorry. So wherever you have a bifurcation point,
Yeah.
you should think that there is an R applied to it.
Right.
So this means that if the number of lines associated with the Grassmann field associated to that vertex is 6 or more, nothing happens. If it's 2 or 4, this means that you have to apply the subtraction. You have to look not at the whole thing, but only the whole thing minus the subtraction of the local parts. Yes, thank you. More questions? Okay, so we are left with checking this. How can we ever check something of this sort? So the good thing of this scheme is that as long as this estimate hold, and this kind of estimates certainly hold for the first 10 iterations or something, not only this bound is valid, but you also get a recursive equation for zh and lambda h in terms of a so-called beta function that admits bounds exactly of the same sort. So this procedure implicitly tells you what is lambda h. Lambda h is the sum of all guys of this sort with lambda h is equal to the sum of contributions of this sort. So it gives you, if you act iteratively like this, lambda h itself is expressed in terms of convergent tree expansion. The only difference being that at the last vertex, the one immediately to the right of the root, you have to extract the local part with four external legs. But the bounds of this guy, the important thing is that all the other guys have an arm acting on the bifurcation points, and this is bounded exactly in the same way, with in particular this prefactor here, which is replaced by 1 because L is equal to 4. Okay, if you write it, you can write. You get the trivial contribution. The trivial contribution is this, which is equal to lambda h plus 1 plus trees and this is what will be called the beta function. This beta function depends on the whole sequence of lambda h plus 1, lambda h plus 2. But the memory of scales that are far away from h is exponentially decaying, because this tree expansion is exponentially convergent in the scale jumps. So the memory here is exponentially damped. So this is essentially you can essentially replace everything by the lambda on the next scale. Not exactly, you have some exponential. And the capital Z, or more precisely the zeta h admits a similar representation. With the difference that now is equal to 2. Okay, so I hope it's clear. So so the quadratic local part, you remember at the specific symmetry structure, which is proportional. In particular, you can extract a proportionality factor zeta h, that is what you can compute out of an expansion of this sort, and this is the beta function for the wave function renormalization. The good thing, once again, is that this function, as long as these bounds on capital ZH and lambda h are valid, this beta function can be bounded exactly by the same kind of bounds like this. So as long as things go well, you can continue to go on and control the recursion by a convergent Okay, so now you have to check what happens. So you have to compute. You have to compute the beta function. So okay, as everybody, you start to compute the lowest order diagrams. So let's start with the lowest order diagrams are those associated to trees of this sort. So in Feynman diagrams is just for Z, the lowest order diagram is exactly this thing here. So you remember this is something that I mentioned on Monday. Here this is the single scale contribution. So this is a lambda h, this is a lambda h, and these are propagators on scale h. If you compute this, you sit down and do it, you get a specific constant. Okay, no, it's not exactly a constant. You get ch lambda h squared, and ch is a constant plus something exponentially. So c minus infinity is positive. You can compute it. It's I don't know, 1/16 pi. Oh, okay, something. It's something you can really compute. Okay, what about the beta function for lambda? Beta function for lambda. Let's again look at the lowest order contribution. So the lowest order contribution again is given by the same tree, but you have to compute it with. So you have to contract in all possible ways in such a way that this is subset of lines with scale larger or equal than h, at least one scale h. Lambda h, in such a way that you have 4 external lines. So what you get is this kind of diagram. Okay, and you have to compute it. Actually, you have to contract in all possible ways. So all possible ways all have this structure, but there are different ways in which you compare fields, and you have to be careful about it. Okay. Yes, I was planning to really do the computation, but maybe I won't. Otherwise, I won't get to the point. It's very. This is a highly recommendable exercise. Let me just sketch it. You have. You see, you start with this guy and this guy. Well, you have to choose, at the end of the day, you have to choose 2 guys to pair with 2 guys in such a way that the external guys have exactly this kind of labels. So you're only interested to pick up external, in all possible ways, the leftover fields in such a way that the leftover labels are like this. So you have to pick up one of the leftover fields that you are not contracting to be psi plus of plus, say this one. One guy that should be psi minus of plus, say this one. And then you have to choose psi plus of minus and psi minus of minus. So there are essentially 2 things you can do. You can either choose this and this, or the other way around. You could choose this and this. So these things are those that are not contracted. so there are a number of, I'm not sure you are following, but anyway, so what I'm saying is that you have to decide which are the guys that are not contracted and contract the others in all possible ways. If you do that, you get that essentially up to a combinatorial factor in front. What you get is the following. You have to be careful about the sums, of course. So the local part you're interested in is sum over y of combinatorial prefactor, maybe an overall sign, and this thing here. Exercise check. I mean, if you're interested in some details, this is the first thing you should really try to check. So notice xy, yx here. So the point is that GH, remember, is almost odd. It would be odd if the propagator was exactly 1 over the omega of k. There is a small rest, so it's not exactly odd, but is odd at dominant order. So at dominant order, these two guys cancel. So out of this cancellation, you get a contribution only from this small remainder associated with the non-linear part of the propagator, which has an additional 2 to the h compared to the usual bounds. Yes, so maybe let me check one thing. So dimensionally, if you don't take into account any cancellation, this guy scales like 1. Because remember, GH of x is like 2 to the h e to the minus 2hx. So this guy is like sum over y of 2 to the h, 2 to the h e to the minus 2 to the h x minus 1. So this is 2 to the 2h times 2 to the minus 2h, as it should. So this guy, the contribution would be, if you don't use any cancellation, would be order 1. But there is this almost parity cancellation that tells you that actually is better than that. So thanks to parity, thanks to this cancellation, this diagram, actually the sum of the diagrams obtained by contracting in all possible ways, this is better said, sum over ways of pairing, is smaller than 2h. So this tells you that the beta function second order is not exactly 0, but almost so. It's summable. So you see, if you could trust this computation, you would get a recursion of this form. Which is very good. I mean, this would tell you that lambda h, uniformly in h, is lambda 0, 1 plus. Okay. Okay, but this is just a second order. So it could be that if you look at the third order computation to the beta function of lambda, that is lambda cubed, but without the 2 to the h. Then you would be lost. So what happened? Okay, so this is a story that was started by Benfatto Gallavotti at least with this approach in the early 90s. The poor master student of Gallavotti at that time, who was Vieri Mastropietro, had as an exercise, starting exercise for his master's thesis, check if he could make the thesis with Galotti was to compute the third order. So the poor guy made the computation of third order and was order lambda cube 2 to the h.
But he also had the spin, right? Not just.
Yeah, he had a lot of things. In fact, Galotti was really perverse. Anyway, so he got the 2 to the h. The hope was to see that this 2 to the h comes from a simple parity cancellation of this sort. But this is not the case. So for the third order already you have plenty of diagrams and the mechanism is much more subtle than just parity. It's not parity. Okay, then there was a even poorer next master student who got the fourth order and then left research after that. But anyway, so this is not a good route to really try to go into third and fourth order. So the better strategy a posteriori is the following. So I will try to sketch. Because, yeah, you see, if we could prove that a tall order, beta lambda, is smaller than, so the sum of all orders, if we could prove that it is like this, then we would be done, because the iteration of lambda would produce exactly this sort of result. The iteration of capital Z also would produce the promised result, and we would be happy. So this is the kind of asymptotic cancellation of the beta function that we would like to understand. Okay, so let me sketch in the last 10 minutes or so what is the strategy. If you have questions about this already, please ask. Okay, so what's the idea? So first of all, you want to, also in this case, the idea also always try to first select the really dangerous part. So what's the really dangerous part? So the really dangerous part is, if you are not zero, the one associated with the propagator that is exactly homogeneous. So you see here, the exactly homogeneous part is 0, the rest has the dimensional gain. So let's look at the part associated with the exactly homogeneous propagator. So at each scale, let's decompose G H of xy, the propagator, in the following way. So the exactly homogeneous one remember, the real one was this plus a rest order k squared. So I isolate this one, which is a sort of relativistic. This is a sort of relativistic or Dirac propagator. Okay, for those of you who know the relativistic or Dirac theory, this could be useful name. Otherwise, it's just a name. So this is the relativistic part or homogeneous part of the propagator, and then there is a rest, a remainder propagator. Maybe subdominant propagator. Yes, S for subdominant. The subdominant part satisfies bounds that are similar to the original one with an extra. Remember, the original estimate of the single scale guy was this. The subdominant part has a 2 here instead of 1. H is negative, so this is a good term. Correspondingly,
You divide by Z or not? How
Yes,
should
yes.
we-
yes. correspondingly, we decompose beta lambda h in beta lambda hr plus beta lambda h subdominant. Okay, beta lambda hr is given by the same kind of tree expansion as before, but everywhere you see written gh, you replace it by gh relativistic. Okay, the subdominant part is the difference. Okay, not surprisingly, since the tree expansion is convergent, this is a convergent expression that scales like 1 times an additional 2 to the h coming from this. So not surprisingly, this guy here is very easily bounded by c lambda h squared 2 to the h. So this part we can neglect to the purpose of looking for. So the really dangerous, potentially dangerous part is the one which has all homogeneous propagator. This is the one in which you could hope to find cancellations. For instance, already at second order is the one that leads to the exactly zero contribution. Okay, so now the remark is that this beta function is the same that you would get for another model, repeating another model with exactly homogeneous propagator if analyzed with these multi-scale methods. So this is the beta function that you would obtain by the same multi-scale procedure. For the following model. This R stands for relativistic. I will now define what this is. There is a question.
Yeah, the question was how you did the decomposition of the beta function? I lost it. I mean, in the first one, there are only the relativistic propagator. In the
And the rest is what you get.
So at least one.
At least one. So you have this this enormous tree expansion. This tree expansion is if you evaluate the value of each family of contribution associated to a tree. This, you remember, is a product over propagators, product over determinants. So you could have in all this thing, you could have just one different, one subdominant. It's enough because you see, first of all, you don't have. So if you add and subtract in a sort of telescopic way, you don't get so many of these terms. You get order n terms out of the telescopic decomposition. And it's enough you have one to get a 2 to the h that goes in front of everything. So that's good. So once you so publicities of the trees, publicity for the trees. So once you worried about the estimates of the trees, etc., then the trees are very flexible to get all the extra estimates you may need in the following. Of course, this is a biased perspective. Okay, what is this guy? So PZ. PZ are smaller or equal than n deep psi is the reference Gaussian integration with propagator 1 over z
Why you change the label now? You use N and not H.
Yeah, I will explain.
Notes in real time.
It's making me hard work. I try to slow it down.
Okay, this N now should be thought of as ultraviolet cutoff. So eventually, N2 plus infinity. And this V of psi is equal to a bare coupling lambda infinity, the integral dx. So this is yeah, okay, now these are really integrals. So we are in the continuum, not on the lattice anymore. So this is G x y divided by c. And V is rotationally invariant smooth potential, say C infinity 0 or exponentially decaying potential of strength 1. Okay. So for those of you who ever saw things of this sort, this is a relative of the Tiering model or of the Lattinger model. So the Tiering model is what you would formally get by replacing this with the Dirac delta. Of course, you have to be careful if you really want to do that. The Lattinger model is what you would get by taking a non-rotational invariant V, rather to be a delta function in one direction and non-local in the other. This is a sort of more invariant. Oh, okay, it's a rotational invariant version of those.
Sorry, Alessandro,
Yes.
but can I ask you a question?
Yeah, sure.
So, but in Lattinger, omega tells you about the chirality of the fermion. I mean, the velocity changes with omega. Well, here,
No.
I mean, you have two branches, right, with the dispersion relation. So in one case, the velocity is +1. The other case,
Yeah, it's like the omega index that was inside.
Yeah, but for you, omega is an overall. Maybe I don't remember the definition of the omega. I mean, the omega is overall factor that depends on omega, and then the relative sign.
No. So for us, omega enters like this. So if you want to put it in a form that is more similar to the the standard Lattinger of Tiering has coordinates that are rotated 45 degrees with respect to ours.
I missed the.
Yeah, so this is k1 plus k2 plus omega k2 minus k1. So this is what usually it's written in this form. Okay, what's the advantage? Okay, so what's the message? So this model is another model. This is a model in the continuum. Yes.
So I mean, this expression does not make sense. No, we are. I mean, you take integrally over all space.
Yes, doesn't make sense. So you have to put other cutoffs. This was one cutoff. So you see, I already have times minus 1 minute. So the point is that this is a theory to which you can again give sense exactly with the same kind of methods. You have to put all the required cutoffs and get uniform bounds in the cutoffs, eliminate them. So for instance, you should put a volume and then take out the volume. But this is very easy. This is the same kind of discussion that I didn't do in the lattice model.
So I mean, what you're saying is that the tree graph expansion that you developed just doing formal algebra from this thing makes perfect sense.
Makes perfect, exactly. So in particular, if you define the trees for the iterated effective potentials for this theory, this makes perfect sense. Okay, and not only it makes perfect sense, but if you write the beta function for this guy in the infrared limit, is exactly the same as the R part, the dominant part of our beta function. So okay. So if you don't say anything about this guy, you didn't gain so much. The point is that this is an exactly solvable model, and this is exactly solvable in several different ways. To be honest, so for instance, there are ways to solve this by bosonization, to pass to bosonic variable and recognize that in bosonic variables this corresponds to a quadratic bosonic theory. To be fair, so if you want to, so this is a subtle point. So if you want to be honest, the solvability by, for instance, bosonization requires a specific choice of the cutoff. So if you look to the papers where bosonization was developed, for instance, Mattis Lieb for Lattinger, previous papers by Johnson for Thirring and many others. To obtain bosonization, you have to perform the, so it also must be said in that paper is not discussed precisely what is the choice of the procedure in which you remove the ultraviolet cutoff. But if you track what they do is valid with a specific procedure of elimination of the ultraviolet cutoff, which is not exactly the same we need here. In any case, this model is solvable up to details, but these details are important about the ultraviolet cutoff, either by bosonization, or it can also be solved purely in fermionic variables. This is something that, as far as I know, was recognized by Benfatti and Mastropietro, at least at the level of mathematical physics. I mean, there were ideas of the sort that Benfatti and Mastropietro used that were scattered around a lot of theoretical physics papers, but the purely fermionic side of the solution using word identities, Schwinger function, and computation of the anomalies in the word identities is due to Benfatti and Mastropietro. At this point, I unfortunately have to stop. It's really a pity.
Benfatti did for the case when delta function for the V or generally rotational invariant V.
So Benfatti and Mastropietro did for both cases, but the easiest, if you like, is for V rotational invariant. But the procedure applies also to the Thirring model. For instance, there is a paper by Benfatti, Falco, and Mastropietro in which they construct the Thirring model solution out of this kind of procedure that I didn't discuss.
Alessandro, I forget what time we have to get to lunch by, but I mean,
now,
we could let people...
5 minutes ago.
No, I know that's when you have to finish, but I was going to suggest that anybody who wants to leave should leave.
Yeah, in fact, I think if you're interested, I think with half an hour more, I can give some more details about this story.
Do we still get to lunch if we have half? Does anybody know when Churchill is open till?
I think it's still open half an hour, but there's going to be a long line.
A long line.
We can also do it immediately after lunch. I'm here until 4:30. So anybody who's interested, we can meet at 2.
Yes.
I don't know.
Sounds good.
Or we can go
So for those who are not interested, okay, maybe you're not interested by this comment. So just to conclude, so the logic is that the beta function is the same as of this exactly solvable model. This exactly solvable model is solvable. So the theory of the exact solution of this in fermionic variables is very interesting by itself. It's a bunch of works, mainly by Benfatti and Mastropietro. But so you work it on a side. Once you worked it out, you have exact explicit formulas for correlations, from which you can obtain as a byproduct a lot of things. One byproduct is the vanishing of the beta function. Good, but not only that. You have very explicit formulas for density-density correlations, which are the objects that you need for the, so if you read them in real space, these are what you need for the fine asymptotics of the dimer-dimer correlations I had at the beginning. So the point is that, so if you remember, the goal of everything was to compute the fine asymptotics of the dimer-dimer correlation, from which we got the logarithmic growth of the variance. So the point is that these are the same as for this lattice model plus b sum over omega minus 1 x minus y x omega x minus omega plus 1 omega psi minus y minus omega lattice model plus subdominant terms. These are the subdominant terms of the same sort of the 2 to the h terms. And this decay like 1 over dimensionally better by 1 power. Okay, so we get a very fine asymptotics from which we get logarithmic growth of the variance and the critical exponent for this second term. This all comes out of the evaluation of these correlation functions, because again, all the inferred behavior of our theory is the same as the inferred behavior of this theory, which is exactly solvable, plus dimensional gains. So this is what you get. Last comment. If you only use the comparison this way, this prefactor A and B are unknown, are just series that you can prove to be analytic, but not more than that. If you want to recognize that this guy is the same as the critical exponent appearing in the second guy, this was the Alday relation that was mentioned. Then you need an additional thing. You need to recognize that your lattice theory has an exact lattice word identity, coming from the fact that you have a local conservation laws of dimers. At each site, there is only one exiting dimer due to the closed vacuum condition. This induces an exact lattice word identity for the lattice model. If you compare this lattice word identity with the asymptotic one of the reference model, you even manage to set one prefactor to, you can even put in corresponding prefactors, and this leads to this. So the additional information hidden in this identity comes from recognizing that the lattice theory has also an exact word identity on top of the other things. I think I stop here, and for further details we meet up for those who are interested.
Okay, very interesting.